Hi everybody, welcome. Hi everybody, welcome to a new and almost last lecture of artificial intelligence. I mean, it's the last lecture in the sense that it's the 14th lecture, but next week we will have still the lecture or a lecture because we will not finish robotics today. We might not even be able to finish the robotics section at all, but this is not a bad thing because the robotics section has no exercise. So of course, if this section has no exercise, there will not be any question in the exam where you have to calculate anything. So the only exam questions from this section can be like general questions like what are the 3 laws of robotics, or what are typical robots, what are typical sensors, how do you do localization of a robot, and things like that. And yeah, before I start, one more announcement. So today is also a special day because we will announce the winners of our Common Road Challenge. And we will also have like presentations, I guess. Edmund, are you ready in the call? So, or Ivan, Edmund will join probably after the break, I guess.
What was that? Sorry, I didn't listen.
That's correct, right? So
I didn't talk.
Okay. So yeah, in case he's not appearing, then we will have to delay it by a week. But I think we agreed that it's today. But let's see. Okay, good. So let's start. As I said, this will be a more entertaining lecture with not much math, but a lot of videos. And we will have a lot of exciting topics. First of all, we talk about robotic hardware. Of course, AI is something that doesn't have to be materialized. So it could just be software. Yeah, and software is not material, is immaterial. And but of course, you can use it also in a robot, which changes the physical world. And we will also talk about how the robot will perceive its environment, and talk a little bit about typical sensors and how these measurements are interpreted. Then we talk about path planning of robots. So for path planning, we will also define the concept of the task space and the joint space, so that all path planning problems are unified. We will then particularly talk about planning in uncertain environments, and particularly if the movement is uncertain. And after that, I will present planning in uncertain environments, where we'll present our own research, where we prove that our actions are always safe, and the robots with our methods would be certifiable, which is of course critical. Without such a certification, you wouldn't be able to sell the robot. And yeah, then also then we will give you a crash course on control of movements. This is a crash course on control theory for robotics, but it will not be very detailed. If you want to know more about these things, you should attend the lecture cyber-physical systems in the summer semester. And then we briefly talk about application domains of robotics. And the content of this section is covered in the AI book in the section robotics. Good. So what are the learning outcomes? So you should be able to categorize robots into the main categories, which are manipulators, mobile robots, and mobile manipulators. I'll also give you some examples, but many of you already know these categories. You will understand the difference between passive sensors, active sensors, and proprioceptive sensors. That's actually very easy. Passive sensor means the sensor doesn't have to have or send a signal out to perceive the environment. In active sensors, this has to be done. In proprioceptive sensors just means that these sensors measure the state of the own robot, essentially. Then we have talked a little bit about some mechanical aspects. So you will be able to determine the degrees of freedom of a robot. And you can determine whether a robot is holonomic or non-holonomic, which is a direct consequence of the degrees of freedom of a robot. You will also be able to explain the difference between sensing and perception. I mean, sensing is just essentially physically sensing, like something like the pixel of a video image, and perception is then the interpretation, like finding a person in the image. You can explain the difference between deterministic and stochastic transition models for robot localization. That should be easy for you because we talked a lot about deterministic and stochastic transition models when we talked about Markov decision processes or reinforcement learning. You can explain the terms workspace, configuration space, forward kinematics, and inverse kinematics. This will be important for motion planning of robots. And you can explain important planning concepts like cell decomposition, skeletonization, replanning, and robustification. And finally, you can explain the basic concept of feedback control. Okay, so let's start. First of all, let's start by defining what a robot is. So typically, this is defined very generally because, like, an autonomous vehicle is also a robot, or like a classical robot in industrial sense, or essentially everything that changes the physical environment or that manipulates the physical environment intentionally is called a robot. And the thing is, like, often these robots are built like as electromechanical devices that are controlled through some computers. But in theory, you could also do the control of the robot using steam pipes, or, you know, I mean, or use only mechanics. So there have also been like old developments of mechanical calculators, and that these could also be used in theory to build a robot. Of course, nobody would do that anymore. That's why this definition is technology independent. But in general, as I said, these are typically electromechanical machines. I mean, yeah, guided by a computer program or electronic circuitry. Essentially, we can take the picture from the first lecture where we discussed like the action perception loop. Like, you have an environment, you have physical quantities observed by sensors, which translate them into signals. Then an intelligent agent has these input signals, produces output signals, which are forwarded to some actuators or effectors, which then change physically the environment. And the robot is nothing else like as an intelligent agent plus sensors and actuators. And yeah, so this is really the general definition. And before we start with categorizing the different robots, we can also talk about first the 3 laws of robotics, because yeah, every roboticist should know these, and they are actually quite timeless. And interestingly, they have been first written down by a science fiction author called Isaac Asimov, who's a Russian who then immigrated into the US. And he was actually a professor for biochemistry, but he also wrote a lot of science fiction books and books in general. I think he wrote, or he was not necessarily maybe the first author, but I think he worked on more than 500 books during his lifetime. So he was very productive, but also, like, he was an old school guy, and he would not have survived the Me Too debate recently. So he was not very respectful to women. So that's a little bit the downside, but the laws he posed were like timeless. So I start with the first law, and then you can continue with the other laws, because I think many of you know those laws. So first of all, a robot may not injure a human being or through an action allow a human being to come to harm. So if a human being is injured and needs help, the robot should help. Who knows like the second law of robotics? Maybe just type it in the chat.
So Edmund is in the call now. If you
Yeah.
Okay.
I see
you
it.
noticed, okay. Okay.
Yeah. Not modify itself, actually. That is all right. So the robots can improve on their own. That is allowed, but it's a good idea. The interesting thing about also the modular robots that we developed and for which we have the startup now, is that using modular robots, you can also, the robots can change themselves, right? So this is quite interesting. Yes, the robot should obey what it's told to do. There's just one exception. So if you tell the robot, kill my neighbor, then the robot is not allowed to do that. So it has to obey all commands, but it cannot be, it's not allowed to violate the first rule. So robot must obey the orders given to it by human beings, except where such orders would conflict with the first law. So you cannot say, kill my neighbor or something like that. Okay, and who knows the third law? Yes, so it should protect its own existence unless it's in contrast to law of 1 and 2. Sorry, I have to sneeze in a minute. Okay, so it's like if like the order of the human would be don't protect yourself, then the robot would not be able to protect itself. Okay. Yeah, so then I mean the rules are quite meaningful because they protect us, so which is a nice thing, especially like in science fiction books, also like in the 40s, 50s, 60s, people already hypothesized about the problem that machines could take over the world. I mean, we discussed this in the first lecture, also when we discussed singularity. And these laws, if the robots would be implemented this way and these laws would be respected, then of course this wouldn't happen. And to ensure that this will not happen, you can use formal methods which prove correctness, which is like what I mentioned at the beginning, one of our main research themes at the chair, and I will say a little bit more about it later in this lecture. So now let's talk about the primary category. So let's start with the robot that's produced the most, which is a manipulator. It essentially means it's a robotic arm with a fixed base. These robots you find a lot in factories, like in a car factory or any other factory. And then there are mobile robots, sorry. So for instance, here you see on the right side, this is a cargo robot, which takes like containers in the harbor of Hamburg. And also autonomous vehicles would be in this category. So they don't manipulate objects, but move them around. And or not only objects, but also humans, if you consider a robotic taxi. And then of course you can combine both categories. So what type of robots can you come up with which would be a manipulator and also a mobile robot at the same time? Maybe you can provide an example. Right, so humanoid robots or like a manipulator on a mobile base would work. And these are very general robots. At the time when like Asimo came out, so it was like, I knew a guy who had it in his lab, but it cost more than 1 million euros. So these can be very expensive and they are not that capable. So like 20 years ago, many researchers said, okay, give us funding for humanoid robots in 20 years, they can work in your household. So this hasn't really happened. I mean, these robots, of course, get better and better, and eventually this will be possible. However, I would not expect that to happen maybe in my lifetime, but maybe in your lifetime, you're a little bit younger. When you're older, it might happen, but let's see. I mean, they will not do everything, but maybe some specific tasks. It's kind of interesting to see how it progresses, but it will not happen fast because it's super complicated to make a robot work in a household. Yeah, I mean, the robot dogs, like there's this dog from Boston Dynamics. I will also talk a little bit about Boston Dynamics later on in the lecture. And there was one guy who wrote, didn't Asimo himself write fiction about how these laws can be circumvented and exploited? Actually, I haven't read any of his books, to be honest. If you know the book, maybe you can put it in the forum and I would like to have a look at it. And I would be interested in how this can be circumvented. So just generally, I would be interested. Okay. Good. So then let's continue. Yeah, let's talk about challenges in robotics first. So if you can remember at the beginning of the lecture, we talked about the classification of environments. So we said that, okay, environments can be partially observable or fully observable, and in robotics usually have partially observable environments. So it's not like a crossword puzzle where you know all the states of the environment. Some things are just hidden, or if you just know the position and observe the position, you have to guess the velocity of an object. So it's certainly not fully observable. It's also stochastic and not deterministic, making it more difficult because deterministic environments are easier. Like if it's fully deterministic, you can just rely on planning and don't need, for instance, Markov decision processes and don't have to find policies to solve a problem. Nevertheless, you can still use planning in dynamic environments if you predict already what the other objects might do. Then it's dynamic and not static, which makes it also, which is also the harder case, and it's continuous and not discrete, which is again the harder case. And also they're usually sequential, the environments for robots, and not episodic, and multi-agent and not single agent. Multi-agent doesn't always have to be the case. There are also many single agent cases, like if there's the Mars rover lands on the Mars, not any other robots driving around. This is a single agent case, but still challenging. And there are other single agent cases, but it can often be multi-agent. So besides the environment, what other challenges can you think of in terms of robotics that you don't have in some other AI problems? Yeah, so you need feedback control, that's true. It's not on the list, but it's something you don't need in many other AI problems. Yeah, the cost of building a robot, or yeah, having physical maintenance and so on, that's correct. That's a disadvantage, but it's also not on the list. I have even more severe problems in terms of the development. Limited computing power, yeah, that's also a problem. What else? Yeah, unstable sensor measurements, correct, that's also a problem. Yeah, so so the first thing I would like to discuss is, let's say if you want to do reinforcement learning like we just discussed, and in many cases you have to do it on a real system, because if you do it in simulation and transfer it to the robot, it doesn't work anymore because the sensor is different, or it's differently calibrated. You have friction in the joints and so on. So, but if you test this in the real world progress is not faster than real time. In a simulation, let's say if you do test drives for autonomous driving, you can drive millions of miles in a day, which is not possible if you do this in reality. And for many real robots, you have to do these time-consuming tests. This is an issue that you don't have if you, like, say, use machine learning to suggest a new movie on Netflix, or if you want to evaluate some knowledge base according to use logics to infer new knowledge from knowledge bases or things like that, then you can always do this faster than the normal time. And the time, it's not only that the tests are time consuming, but another problem is that they have to be real time capable. So many tasks are time consuming, like the end queens problem, or constraint satisfaction, logics, probabilistic reasoning. But you cannot just wait forever, because if the robot should interact with humans or the robot should do a task, it has to be real time capable. It shouldn't just stand there and compute for an hour and then perform an action. And then robotics is very interdisciplinary. So you have researchers from mechanical engineering, electrical engineering, computer science, ergonomics, cognitive sciences, and psychology. And bringing these people together is not trivial. Also, like as you know, at the end of the year, the Department of Computer Science will not exist anymore at TUM. Are you aware of this, by the way? I mean, maybe not to shock you too much. Okay, yeah. Okay, so the thing is like, so like is a longer vision. The TUM gets rid of all the departments, and the departments are fused into schools. So mathematics, electrical engineering, computer science will fuse into CIT, computation, information technology, will be in a new school. And then there will be, there will be not like Fakultäten or which is now, but there will be other departments. So there will be a department for computer science and for mathematics and electrical engineering, but a fourth one for computer engineering, where also the robotics researchers and our group will go. And now we are in the transition phase. So both the Fakultät Informatik and CIT exist now in parallel, but the website and everything hasn't changed yet. But by the end of the year, all this will completely change. So there will be just the CIT school, and it will be easier probably in some sense, especially if you're doing a PhD, to do interdisciplinary research then. So this is one of the goals of this fusion. End of the year, I mean, no, end of like the calendar year. So at the beginning of the winter semester, we will only be CIT. There will be no Fakultät für Informatik anymore. So is it a good thing or a bad thing? I will not comment on this because the lecture is recorded, but it's what I can tell you is that it will not be a tremendous difference compared to what we have now, but it will be different. Okay, you can ask me this in private conversations. Okay, good. Okay, so now let's talk a little bit about sensors. We don't go into details how the sensors actually work and what physical principles are behind them. It's just a little bit a general discussion. Again, if you want, what are typical sensors that are used in robots? You can just type suggestions in the chat. Actually, everything you write would be probably fine because there's almost no sensor which is not in a robot. Yeah, like camera, LiDAR, encoders, radar, camera. Yeah, these are all in robots. Very good. Maybe I wait for 2-3 more. Ultrasonic sensors, correct. Temperature sensors, correct. Yeah. Also like tactile sensors for skin and so on. Force sensors, right? Very good. Good infrared distance or good sound. Yeah. So here's just a selection. This is not exhaustive. It's just a list which rather well represents different types of sensors, like acceleration sensors, especially for mobile robots. That's interesting, but also for humanoid robots to get the acceleration of some body parts. Light sensors for very cheap sensors, like sensors that just clean the room or like that just have to follow the light for some reason. Of course, usually these light sensors are not used so much anymore. Usually now you just mount the camera because they're so cheap. You don't have to just have a sensor how bright it is. For strain sensors, if you have physical interaction or if you have to manipulate physical objects, it's good to know how much pressure you apply. And sonar, like this is especially good for underwater robotics. Like if you want to have a robot that inspects the sea or wants to find new deep water species or whatever. I also once was in a project where an underwater vehicle was constructed, but I was only briefly involved. Then of course video cameras are used heavily nowadays. This is a kind of an old model, and maybe I should update the picture. Then of course LiDAR is becoming more and more popular because it gets cheaper and cheaper. There's also a Munich startup for solid state LiDARs so that they become bloody cheap. Then pressure sensors, then angular sensors for the angles of the robotic arms. And then of course, also radar, especially for mobile systems and so on. So as I said, this is not exhaustive. And as I mentioned, there are like 3 categories. The first category are passive sensors. So they just detect physical effects, like a video camera just observes the light in the environment. Then infrared camera detects the heat waves, and global positioning system GPS just captures the signal from satellites, and light sensor is like with video cameras and so on. And then there are active sensors like LiDAR or sonar, which send out a signal that is reflected and then recorded. And of course, you ask yourself, okay, why should I invest energy to send out a signal if I can get the signal for free, like in a video camera? So what would be the advantage of using, let's say, LiDAR compared to a camera? Right, night and weather, very good. So like if it's dark, a camera doesn't see much, so essentially almost nothing. Or if it's really, really dark, actually really nothing. And a LiDAR, of course, if you send the beam out at night, it will be reflected, so you can still detect things. And like if you have a bat, if you would be a bat, you also shout, they use sonar, and then hear where things are reflected, so you can also orient yourself at night. And also you often get a more precise signal, like because you can exactly detect the amount of time it takes to, that the signal is reflected. You get a very precise measurement. Like if you want to know the distance, if you use video camera, then you have to use usually 2 cameras, like we have as humans. Like we don't have cameras but eyes, and then you can calculate the distance based on the distance of the eyes. You just maybe, I mean, it's a simple geometric argument, and if you find the same point in both cameras, then you can calculate based on the distance of the cameras where this point would be. But it's of course not as precise as using active sensors. And proprioceptive sensors are very different. Like these are the sensors you use to inform the own robot about its own state, like the angular sensors, acceleration sensors, force sensors, pressure sensors, and so on. So these are the 3 main categories. Okay, so let's continue a little bit the general discussion. So because robots are physical devices, we also need to talk a little bit about mechanical engineering. So everybody who studies mechanical engineering had this in the first semester, which like, yeah, so we're talking about the degrees of freedom of a mechanical system. So these are essentially the number of independent direction in which a robot can move. So let's say if we consider ourselves as to be a robot and we are moving on a flat surface, then we only have 2 degrees of freedom because we can only go in X and Y direction. Let's say we have a Cartesian coordinate system, and any other point or direction we're moving can be expressed linearly, or it's just a linear combination of the X and Y coordinates. So then we would have just 2 degrees of freedom. Of course, in 3-dimensional space, you can have X, Y, and Z coordinates. But in order to fully specify the position of an object in the space, you need more than that. So this is like a measure tape, was just lying on my desk. So to fully specify its position in space, how many degrees of freedom do I need? Or how many degrees of freedom does this tape measure have? 6. Okay, yeah, that's correct. So it has 3 rotational and 3 translational degrees of freedom. So I can move it in X direction, in Y direction, Z direction, and I can rotate it in this direction, and in this direction. So if you look at an airplane, then this also has specific names. Like forward would be longitudinal direction, sideways would be lateral, up and down would be vertical, roll would be if the plane flies in a curve, and yeah, rolls to the left or right, then yaw would be the orientation along the vertical axis, and pitch would be along the lateral axis. So pitch is, you pitch up if you take off, and if you land, you you still pitch up in an airplane, but you go down if you want to lose elevation, essentially. Okay, good. Now we can combine several objects through joints. Simple examples, our own body, like here the elbow is a joint. It's actually a revolute joint, which is the first joint you see here on the right. And this has just 1 degree of freedom. So what it means, let's say if you have 2 objects, each of them have 6 degrees of freedom in 3D space. And then this joint fixes 5 degrees of freedom and leaves 1 free. So then that means that the first object, of course, has 6 degrees of freedom plus 1 more degree of freedom. So that these two objects together would have 7 degrees of freedom. And of course, if you would fix the first object, you glue it to something, so then all 6 degrees of freedom are fixed, and then you just have only 1 degree of freedom, which is the rotation of the second object. So the next would be a prismatic joint, which is shown here below, meaning it's a joint which can only move translationally, so in one direction, so it can only move in one direction. And the third one would be this helical joint. How many degrees of freedom does it have? So it's like if you have a screw. How many degrees of freedom does a screw have? Right, only 1, although it rotates and translates, but they are coupled. So this is why a helical joint or helical joint, I have to check what the correct spelling is actually, has just 1 degree of freedom, because there's a linear relationship between the orientation and the displacement. So this next joint here shown below the screw, how many degrees of freedom does it have? 2, right? So it has 1 rotational degree of freedom and 1 translational degree of freedom. So 2 degrees of freedom. This is a cylindrical joint. And then we have here a spherical joint, the last one, which is shown. How many degrees? Just you can type it if you like. 3, yeah, it has 3 rotational degrees of freedom. This is what we have at the hip. So when the leg leaves the hip, this is a cylindrical joint. Also, like our shoulder, you can rotate it, and you can also rotate it this way. It's essentially it's not a perfect cylinder, but it's essentially you can abstract it as a cylindrical joint. And then, sorry, as a spherical joint. And there's a planar joint, which is hard to visualize, meaning that you have 3 translational degrees of freedom. Okay, so here's an example of a very famous robot. I think it's the Stanford configuration. So you have 5 rotational degrees of freedom in 1 prismatic joint, which is 1 translational degree of freedom. So overall, at the end effector, you have 6 degrees of freedom. And obviously, most industrial robots have 6 degrees of freedom because you can put any solid object in any configuration, like translationally and rotationally, which is good. And of course, yeah, let's discuss what happens if you have more than 6 degrees of freedom, whether this is useful. So 6 is the minimum number required to position end effectors arbitrarily. And now we have the first feedback question of today. Does the human arm have more than 6 degrees of freedom? And you can already start the link, and there is a trick how to determine this. So you can put your hand on the table or somewhere else, and you fix your shoulder, and then you check whether your elbow can still move, okay? And this will help you to answer whether A, B, or C is the right answer. So A would be we have less than 6 degrees of freedom, B would be we have exactly 6 degrees of freedom, and C would be we have more than 6 degrees of freedom.
Okay, so from what I see, around 40% people chooses B and A, and the rest choose C. So there's not too much difference.
Okay, yeah, but yeah, C is correct because so you put your hand down, which fixes 6 degrees of freedom. You fix the position of your shoulder, which also fixes 6 degrees of freedom. And then you have two links, so the upper arm and the lower arm, and they each have 6 degrees of freedom, but you can still move the elbow if everything else is fixed. So that means we have roughly 7 degrees of freedom. And then you can ask yourself, yeah, why do we need 7 degrees of freedom? Because with 6 degrees of freedom, we could manipulate any object already, right? And does anybody know why 7 can be better than 6? Or is this just stupid? Right, so we have some redundancy and more options. So yeah, so we can optimize. So the thing is, let's say if we fix the position of the object we want to manipulate, then we can still move our arm in a way that is more, for instance, more energy efficient. So a typical example would be if you drink a liter of beer in the beer garden. So some people who are already a little bit tired, they you can put your elbow in the in your stomach and then drink. It's easier. Or you can you can just manipulate things and you can put your arms in a position that is more comfortable for you. And that's why we have 7 degrees of freedom. So it actually makes sense. And with our modular robots from the startup, you can even have 7, 8, 9, 10, 12, 15, 16 degrees of freedom if you want. So you can use this a lot also for optimization. Good. So then so Edmund, should we start at 5 or should we start now with the ceremony?
I think we can wait a couple of minutes.
Okay, so then I will finish this holonomic, non-holonomic topic. This is the last topic because it fits the degree of freedom topic. So there's another categorization you can make besides manipulators, mobile robots, and mobile manipulators, and that is whether a robot is holonomic or non-holonomic. And holonomic means that the number of controllable degrees of freedom equals the number of degrees of freedom of the object. And non-holonomic means that the system has more degrees of freedom than you can control. So a typical example, let's say, would be a car. So if you have a car, then on a 2D road, you have only 3 degrees of freedom, right? So you have 2 translational degrees of freedom, X and Y, and the heading of the vehicle. And how many degrees of freedom can you actually influence? So think of driving a car. So how many degrees of freedom? Yeah, somebody wrote X, Y. Yeah, so we have 2, which is the steering. So that's 1 degree of freedom, and we have acceleration. So braking and acceleration is the same, it's just a different sign. So one is positive, one is negative, but it counts as 1 degree of freedom. So we have just 2 degrees of freedom, but the system overall has, so we have just 2 that we can, degrees that we can influence, but the system has 3 degrees of freedom. That means like it's non-holonomic. And that also means we cannot move vehicles like arbitrarily. So let's say if there's a parking spot somewhere, which almost never exists in Munich, I also don't have a car. And but just as a discussion point, so let's say this is a free spot and this is your car. You cannot move your car sideways, right, into this spot. What you have to do is you have to park somehow like this. And that's because it's a non-holonomic system. However, there exist holonomic vehicles, and one of those has been built by DLR. And now I can quickly show you a video showing this. And there are more and more cars who also have rear wheel steering. And if the rear wheel steering would be 180 degrees and the front wheel steering is 180 degrees, you also have you would also have a holonomic robot. So now we have to check. Wait a second. Yeah, there's a lot. So this is the vehicle, and you can see, for instance, it can go sideways, and if it wants to park, you just turn all the wheels, and then you just park the vehicle side. So I think they first rotate just for fun, and after rotating, I think they park sideways. But then, of course, this vehicle has more actuators, right? So it has more degrees of freedom. Actually, each wheel can move independently, and that's why you have at least as many actuators as you have degrees of freedom, and that's why this is a holonomic system. Okay, I guess that's where we can stop. Afterwards, we just talk a little bit about different mobile platforms and configurations. Yeah, I think it's a good time to stop. So I would stop sharing my slides.
Now we'll be holding a small award ceremony for the Commonwealth Search Prize Challenge. I'll first give you a brief summary of the submissions, and we'll announce the winners, have a small ceremony, and following that, the top students will present their solution to the challenge. So here are some figures. As for the number of submissions, we received some 190,000 submissions in total, and out of which 180,000 were accepted by the server. This high acceptance rate was due to the fact that this year we provided the durability checker, which you could already verify your solutions locally. Unlike last year, you only had to submit and see whether your submissions were accepted. And in total, we had 187 students registered at the forum and registered a challenge. And in the end, 138 students actually submitted their solutions. As you can see, most of them passed the exercise. 4 of them didn't have enough solutions, so they didn't qualify the 2 bonus points. So yeah, congratulations to you. You received 2 bonus points. This chart shows the number of solved scenarios. So in the bonus exercise, we provided like 500 scenarios. As you can see, the top student had 450, and the second place had 430, and it goes down up to 380. So yeah, I would say the top student probably have a better insight, or maybe they have a better algorithm. So we'll see in a while how did they solve the solution. And this is the summary for the prize challenge, which the students could solve all available scenarios. And as you can see, the first 2 students actually had a very close number of submissions. It's just a marginal difference. Yeah, again, it will be interesting to see whether their solutions are similar or how did they manage to do so. And here again, we will present some of the selected solutions from the submissions this year. So here you can see that the vehicle, the Eagle vehicle, which is in green, actually enters the Go region. So this is quite normal, as you would expect. And this is a bit more complicated, where the road is a bit curved and you have to make 2 turns. And yeah, it also succeeded in reaching the goal region. Similar to last year, again, we have some maybe somewhat crazy scenarios, not so safe. As you can see, the Eagle vehicle was trying to avoid maybe a motorcycle coming from behind, and eventually it basically just went on to the other lane and almost crashed the other vehicles. This is a similar situation where it was just changing lanes and coming back, and this is essentially not a very safe behavior. But this is still accepted, since in the current stage we don't evaluate like how safe maybe the solutions are. So it's basically, if you reach the goal region within the specified time frame, they will be accepted. Yeah, let's see. Yeah, we still have some similar scenarios like this, where yeah, you just enter the goal region. I think this is a bit crazy, where the vehicle just changes to the leftmost lane and comes back. So yeah, this is definitely something you don't want to do at an intersection. So yeah, I would say this is not the best in terms of safety. We also have something like this, which the ego vehicle doesn't really respect the other vehicle and just cuts in very abruptly and enters the goal region. So these are some of the selected solutions that we have. And if you want to see some other solutions, you're welcome to visit the Commonwealth website and just click on ranking and just click on the name of scenarios, and you will be able to see other interesting solutions. So next we'll announce the list of winners. So we actually wanted to have like top 10, but it happened that 2 of the students had the same number of submissions. So 10 and 11th are actually the same. So we'll have 11 top 10s this year. So congratulations to these students on the list. So as promised, we'll hold pizza night gathering with them. Unfortunately, due to the pandemic, it's gonna be online, but nevertheless, yeah, it's still a nice chance to maybe exchange some ideas and just get some feedback from them. And then congratulations to the top 3 students who will receive a special certificate from us stating their achievements in the exercise. And yeah, now it's the exciting moment. We'll announce the top 1 student, which is Tim. And congratulations to Tim Bayer. Yeah, he was the one with the most submissions. And yeah, he will receive a cash prize from Professor Althoff after the ceremony. So congratulations. And this is just a visual impression like what's going to be the prize. So yeah, congratulations. Maybe Tim, you want to say something, or if you can, Ivan, can you maybe add Tim as a presenter? So yeah, he can shortly also present.
Yeah, I'll try to find him.
Yes.
No, he should be a panelist, I think.
Also, congratulations from my side. And regarding the pizza gathering, we'll do it again. Like, we'll give you some money, and then you can order something to eat and eat at home, and we can still chat online.
Ivan, and could you also please add Michael to the list of panels?
Michael, last name. That's okay.
Thank you for the congrats, and also congratulations to Michael, who obviously also had a really good algorithm.
Yeah.
I don't know who will present first.
Maybe Michael can present first, if that's fine. And then,
sure.
Yeah. Then I will stop sharing my screen. Yeah, then the stage is yours. Looking forward to your solutions.
So yeah, my presentation is for the topic Common Road Optimizing Motion Primitives for the SM1 cars, as this was the metric I was focusing on. So at first outline, I will show what the given motion primitive generator was, then I will show some problems I saw, and then how I solved them, and my results. The given motion primitive generator works basically that it takes the velocity samples and steering angle samples provided by the configuration file, makes the Cartesian product, and tries to map each velocity start and steering angle start to the Cartesian product of the same samples to the end. Then it will calculate the acceleration rate, the acceleration and steering angle rate simply by interpolating. And yeah, then it will try for those time steps configured, for example, 5, to try to simulate the next state. And yeah, if it's not reached, yeah, there's an error on no trajectory for this combination. So the first problem I saw is that the branching factor is very varying. In the low velocity range, we have a lot of decisions for the car because a lot of those trajectories connect and stuff like that. And as fast as the vehicle goes, the less possibilities are there for the car. So for example, this is the default, well, not the default, but the motion primitive file used in the tutorials, and it has a high branching factor in the low velocity range and bad connectivity in the top one. So one problem to avoid this was to just try to connect the neighbors. So for example, if you just try to steer a little bit, and then in the next trajectory you can steer a little bit more, and then a little bit more, and a little bit more, so that we reduce those the high amount of trajectories in the low velocity range. Yeah, so basically the algorithm changed like that. The second problem was that not all the primitives were connecting properly and were not reachable and stuff like that. So what you can see here in the diagram are the are 5 trajectories, which are basically steering angle 0 and accelerating. So from 0 to 4 meters per second, and from 4 to 8, and so on. And the top 2 ones from 12 to 16 and from 16 to 20 meters per second. As you can see, those never reach the target velocity because the car just isn't capable of accelerating that fast. So a solution to that was that we introduced variable primitive times. So at the default one, every primitive was like half a second, and now it will change depending on what it needs. So as you can see here, if the velocity for the start and the end and the steering angle is the same, we will still make this half a second drive straight stay, but as soon as we have some changing, we try to find the fastest trajectory from the velocity start and steering angle start to the velocity end and steering angles end. Yeah, it's basically just trying. It's basically just trying and brute forcing through those steps, such as those trajectories, and yeah, trying to connect those. So with this, we were able to reduce these errors of unfeasible path from 70.2 in the average, from 70.2% to 5.4%. But another problem were that the motion or the trajectory generator tried to generate trajectories for just unfeasible start and end states. For example, driving full velocity with full steering angle is the car is just not capable of doing that. So the idea was, or my idea was, to reduce the max sample steering angle at higher velocities to the maximum capability of the car. For example, with 20 meters per second, the car can just steer a little bit before getting out of control. So in the sampling, we now for the steering angle start and for the steering angle, and we now consider the velocity which was used, such that we can now get into those bounds. And with that, now these two error fields are also resolved, and 94.6% of the trajectories the motion primitive generator tries to generate now will succeed in a valid trajectory. So one problem with this approach is that we will always try to drive the car with the maximum acceleration and maximum steering angle rate that the car can offer. And that's it's not really reasonable for optimizing for the SM1 cost, because those two variables are penalized quite heavily. So I introduced just a simple chill factor to slow the car a bit down and to get everything smoothly. So the AI is not driving like a crazy person. So yeah, and with those, I kind of have here some results from what I created. So these are here the motion primitives. So the 9 provided ones, then 6 which only use the connected states or connected approach, then also 5 more which use this chill factor, and also I had a motion primitive which was basically just do nothing and stand there. And fun fact, it solved 455 scenarios of those over 2000, and was quite successful in regarding the SM1 cost function. Yeah, so as you can see, even though the 9 provided motion primitives can actually produce a lot of valid scenarios, especially for if you optimize for the best SM1 cost, the chilled scenario motion primitives are quite effective. Yeah, so I will now show some 2 of my motion primitives I generated. So this was one of the first one, which does not use the chill factor or the chill factor of 1.0, and it has an average branching factor of 8.6, and the average length of each trajectory is 0.7 seconds, and it provided 24 of my best solutions. And by far the best performing primitive was this one. It's in a velocity range from 5 to 15 meters per second, with a velocity step of 2 meters, maximum steering angle what's possible, with 7 interpolation steps, and with a chill factor of 0.3, and it has a branching factor of 3.5, and provided nearly 800 of my SM1 best SM1 solutions. So that's all. Thanks for listening.
Yeah, thank you. So as I said, there's always a surprise. So like you focused a lot on optimizing the motion primitives, as much as I've never seen before by any other students in the last year. So which shows how much potential there is. That I think was very exciting. Maybe a question is like, if you use the chill factor, of course, and you're in an emergency situation, you might not have the motion primitives for using the full capabilities of the car. So you would then use maybe first the chill factor primitives, and if you don't find a solution, switch to another set, or how would you how would you handle such a kind of situation?
That's definitely a possibility. I just didn't implement it in the search algorithm. So basically my search algorithm, I implemented it quite early, and it's basically just use this given route planner and follow it with the primitives you have.
Okay.
So it's not very complicated, and I think that's quite a nice idea. If there are some dangerous situation where you really have to get out of there, you can drive the car to the maximum.
Mhm.
But yeah, as I said earlier, I was optimizing for this SM1 cost, and this one was basically just drive.
Sure, I mean it's a competition, right? So you can optimize to win, right?
Yeah, I just have to admit I was a bit confused because I didn't optimize for the most valid solutions. I was just optimizing for the wrong stuff. But yeah,
I don't know. I think it's smart because there was this. I mean, as I said, I mean we didn't put a lot of brain power into selecting the motion primitives, so there's a lot of potential that we could use in the next years as well. So thanks a lot.
So thank you for the presentation, and I think we can now hand over to Tim, and he will present his solution. Thank you, Michael.
Right, hi, can you see my screen?
Yes, now it's working.
All right, awesome. I feel kind of bad because my presentation is way less polished. It's a really, really cool approach, really awesome. And it's also quite, you'll see some similarities later on. So I'll just get started. The first thing I did was to actually look at what is asked of us in the problems, because not all tasks are the same. Some or most problems specify a desired time where you need to be at a goal, or even just still be around. So only less than half of our scenarios actually want you to be at a specific place. So half of the scenarios are just survival. Doesn't matter where you end up, just don't crash. And then some other tasks want you to have a specific velocity and an orientation. But it basically boils down to you have survival tasks where you just have to last and not crash, and sort of drive to a goal in time tasks, which are way more difficult because you actually have to get to a certain point. Exactly. The nice thing is if we actually have to be somewhere, we can rule out configurations that cannot make it anymore. So if we're too far away and there's very little time left, we can rule out those configurations very early. And I thought about just basic computer science. So can we optimize the execution speed? Everything is run in Python. There's usually a lot of speed up you can find just by optimizing things. And another nice thing about the difficult tasks that want you to be somewhere is, like Michael did, we can use the high-level route planner that is already implemented for us. And if you give it a scenario and a goal state, it outputs this path like the red one here, which is not perfect. Like you can see on the right, it hits a car. So you can't just drive along the path and expect to arrive safely. But you can obviously use the path to guide the search and stay along this red path. And that's actually almost all there is to it. The final heuristic for this solver uses the route planner and penalizes states that stray too far away from the path. It penalizes states that are oriented differently than the path. So in this case, like we start at the bottom left, and if the car would start to turn too far left or too far right, while the path is still straight, I would say, no, that's bad, stay along the path. And it considers the speed cone. What I mean by speed cone, you can draw a diagram that plots the distance to the goal over time. And you start with a lot of distance to the goal, but also lots of time still to go. And you have to end up with distance 0. So you have to be at the goal in some certain specified time interval. So on the bottom right. Now, what most humans would do, I think, is try to just get there in a straight line. So you don't want to rush to the goal and then wait, and you don't want to wait at the start and then rush to the goal, but you just want to sort of smoothly drive with a constant speed. So states that stray too far from this optimal path are penalized by the heuristic. And we can, like I mentioned earlier, we can introduce hard limits for states that are not able to reach the goal. So we can draw lines here that limit, that show configurations that cannot make it anymore. So if we, for example, wait too long at the start, we'll eventually get into this area here on the right where we can't make it to the goal. Yeah, and on the flip side, I also didn't want the algorithm to rush to the goal and then wait. There's no particular reason for that. I just thought it was nice and it didn't help or hurt performance. So states that are on the bottom left here are also just kicked out. Yeah, and that's actually all there is to this part of the algorithm. I also got sidetracked by optimizing for this SM1 cost though. So after the first part of the algorithm, I started thinking, like Michael did, about finding good solutions instead of just any solution. So I took a look at the cost function, and it's composed of a series of integrals that you can take a look at here. And all those integrals are basically just at each time step, please accelerate as little as possible, stay as close to the lane center as possible, etc. But all of those costs are positive, so you can't ever keep driving and then expect to get a lower cost than you had previously. And this means we can actually search over the cost function using a standard algorithm, because each state is connected via this cost function with a positive cost. Now, I was not able to find a heuristic for this cost function, so I just ended up choosing a naive uniform cost search, which doesn't need a heuristic. And yeah, the problem with that was if you just use the provided cost function implementation, it's really, really slow. So you can't really search a reasonable amount of configuration because all of the time is spent just computing the cost over and over again. So I spent some time looking at the code, optimizing it, added caching, removed copies, etc. And this yields about a 5x speedup, which matters a lot. Yeah. Now, when you run this algorithm, you can, if you give it 20 seconds of compute, you can typically find solutions with costs up to 1,000. And because it's uniform cost, we know that the solution is actually optimal. Now, this means that for any scenario where it's possible to find a cost under 1,000, we know we can find the optimal solution. And before the competition, I actually scraped the costs, the best published cost of all the scenarios, and almost 2/3 of the 2,000 something scenarios have a published cost of less than 1,000. So it's already like you can see that 2/3 of scenarios can be solved optimally with this algorithm, subject to a few assumptions. Like if anyone really cares, you can ask me about it. It's pretty boring. Yeah. And when you plot the solutions that this algorithm finds into the same graph, you see that we can beat the best existing solutions in almost every case. So blue solutions are solutions found with this algorithms that would be a new global best before the competition. Michael probably has quite a few now. And if you play around a little bit more by ignoring some of the constraints that so for example, the start state of a problem setting gives you a position, orientation, and a velocity with which you should start, but it's actually never checked by the server or by the solution validity checker whether you actually use that velocity. And if you ignore the velocity for the start, you can find often better solutions with lower cost. And if you run those, you can see you get even better costs and beat the best solutions almost every time. Now this algorithm does not work for the very hard scenarios on the right here, but that's why we have the previous planner guided algorithm. Now for the final solution, I basically first run the uniform cost search to find nice solutions, which if you give it 20 seconds, finds about 1,000 or 1,200 solutions. Then I run the planner heuristic algorithm, which is an A star, but it uses this high-level route planner, which gives you about 950 additional solutions. And finally, I switched to a slightly different heuristic again, but it's similar in the concept, and that gives you 35 additional solutions, which adds up to 1,985. And that's all there is to it. Thank you very much. And yeah.
Yep, thank you. Very nice presentation. So actually, because you had two very different approaches, which are complementary, right? So one focused on the motion parameters, you focused more on improving the code, making it more efficient and so on, and also finding good heuristics. If you would combine your approaches, we would have kind of a super algorithm, which would be very good. And if you actually want to do that, there is like last year we had the first international common road competition where also other research teams could participate, and we'll have that again as part of the an international conference called Intelligent Vehicle Symposium, and there you can win more money. So now you could just win 200 euros, but there last year we had 3,000 euros, and maybe this year we have more. We even had an offer from Google for $10,000, but I was too busy to handle all the administrative things because it is some foreign sponsor, which is complicated legally. But now this year we try it again. Maybe they still want to sponsor. If you're interested, just
I think it would be really cool if Michael's up for it.
Yeah, we can discuss it during the pizza meeting, or I don't know. Edmund, do you like to add some more things?
Not really, but yeah, thanks for the presentations, and yeah, looking forward to the pizza night gathering.
Yeah, and one more thing, as I mentioned, is we have this practical course for motion planning of autonomous vehicles, where you could continue this. And also, as I mentioned that we are ordering this new autonomous vehicle, which now will be a little bit delayed, but we will integrate all the code into Carla and some other high fidelity simulators so that you can check this. And we also have a driving simulator for those who have looked into this, who participated in the programming exercise. We could also run this on this driving simulators in the future, so you can sit there and see how it would feel to drive while your code is running. And also I will talk to Edmund regarding what are aspects we might integrate in the standard planner for next year, because it's always a good idea to include a few things. Like, for instance, one year we included this high-level planner so that not everybody had to implement this each year. And maybe now we will also use some of your things so that the people can focus on some new ideas, so that over time the standard planner also gets better. Because we don't have right now, I have no PhD student working on improving this planner based on motion primitives. We are working on other approaches, like where we combine reachability analysis with sampling-based techniques or with optimization-based techniques, which is a different approach, and which has this special feature that the more dangerous the situation is, the faster you find a solution, which is especially helpful for certifying these planners. If you're interested, I will talk a little bit about this in our last lecture next week. But as I said, we might not finish all content this year, and I might not be able to talk much about our own research, because next week we will also have our Q&A session. So please, if you have any questions regarding the exam, post them in the forum so we can prepare, and then we can also prepare also the answers already, so that it's just you know, a faster and more nice experience for you. So if you don't post any questions, you can still post them in the online meeting. But if it's better to post them in the forum, and if you have a spontaneous new question, of course you can still ask the question. And then on the last Fridays we will have the remaining exercises. And again, I didn't receive many emails, but please, if I have any questions, always use the forum, because it's always, I mean, otherwise we get the same question over and over again. It's just based on the huge number of students attending the lecture. Like questions like regarding the exam, many are redundant. So if you go to the forum, you already see that many of your questions might have been asked already. And if not, then of course, please post your question. Okay, so I had a lot of fun today. I hope you had too. Thanks again for the 2 nice presentations. Also looking very much forward to the pizza night. And yeah, anything else, Edmund, you would like to add?
Not from my side.
Okay, so then Edmund will, yeah, regarding the prices, we will contact you again to how to transfer the money, and yeah. Okay. So then we are a little bit earlier finished today, but that's not a big deal. Just 10 minutes early. So wish you a nice evening. And yeah, if you like doing research in this area, always contact us. I also told you before, we'll have a startup regarding autonomous driving soon. And also, if this is your last lecture and you have already written your master's thesis, we will have 2 open PhD positions in a few days. For automated truck driving in collaboration with MAN, the truck manufacturer in Munich, which would be a nice PhD position if you are interested in doing a PhD. Okay, so then have a nice evening. Bye.
Bye-bye.